Well, welcome back. Today we're going to continue our circuit conversation by talking about combination circuits. Not all circuits are going to be parallel or series, so we need to talk about what happens when we use a combination of the two working together. In this drawing I've got a light bulb, or what kind of looks like a light bulb, that is drawn in series with two light bulbs that are in parallel with each other. In my second drawing I've got a set of resistors that are in parallel, but within each branch I've got two resistors that are in series with each other. So what happens is we have to kind of combine our rules a little bit, and I'm going to walk through a practice problem of how to do that. The practice problem I'll do will be similar to this first picture. So if I flip over here, you'll see I've got a circuit set up where I've got a 12-volt power source that has been connected to a resistor of 220 ohms that is in series with a set of parallel resistors that are both 470 ohms. So we're going to walk through how I would find the total voltage, the total current, total resistance, the voltage at each of the resistors, and the current at each of the resistors. All right, so total voltage. Because this is my only power source, the voltage is given right there. I know that my total voltage is 12 volts. Total current, we're going to treat this, we'll end up treating this similar to a series problem, but we'll talk about current a little bit later. Total resistance, we'll talk about that right now. So we'll have our resistance of 1. Since it's in series with this parallel system, what we're going to say is we still use the series rules, but we have to say that R1 is in series and it will be added together with the equivalent resistance of the parallel portion. So we'll call that resistance of 2 and 3 is what we'll call that. So I have that the resistance of 1 plus the resistance of 2 and 3. So before we move on, let's work over under here and talk about what that equivalent resistance would be. So from our parallel circuit rules, we know that the equivalent resistance, or R23, is going to end up being 1 over R23 is equal to the sum of 1 over R2 plus 1 over R3. So I'm going to rewrite that as 1 over 470 plus 1 over 470. And when I have that together, let me do my quick calculation here. I end up with 0.0042, and it keeps going on. I'll just leave it at 0.0042. Now let me transfer this down here. So 1 over R23 is equal to 0.0042 ohms. I need to make sure that I don't leave it at that. That is 1 over R23 is 0.0042. So in order to get the actual equivalent resistance here, I need to take the reciprocal. So R23 is actually equal to 1 over 0.0042. So I'll take the reciprocal of that and get 235 ohms. So that is my equivalent resistance of 2 and 3 combined. So I'll take that back up over here and plug into my total resistance. So I'll say I have 220 plus 235, I wrote equals 235, and that gives me a total resistance of 455 ohms. So there's one answer out of the way. That I can combine now, just like I have in the past, with my current, or with my voltage to find my total current. I have my total resistance, I have my total current, I can find my total, I have my total resistance, I have my total voltage, I can find my total current by taking voltage total divided by resistance total, 12 volts divided by 455 ohms, and that gives me a total current of 0.026 amps. So there is my total current. All right, So I've got my total voltage, total resistance, and total current up above here. Now I can go down and work on finding my individual components themselves. And here again, we are going to be combining some of our concepts based on where our components are located. So my voltage at 1, I simply will use the Ohm's law and say V equals IR, so current at 1 times the resistance at 1, which is 0.026 times 220, and I get my answer of 5.8, and that's rounded, but 5.8 volts. Now at voltage, the voltage at 2 and 3, these two are in parallel with each other, and so my voltage at both of them ends up being the same. However, since I'm going through this resistor first, I only get part of this total 12 volts that's over here. So what I can do is simply subtract 12 volts minus my 5.8, whatever's left, from my voltage at 1, 5.8 volts, and that will give me 6.2 volts. And since these two are in parallel, I can say that V3 is simply equal to V2, and that is also 6.2 volts. So it's a little bit tricky here because I have two different rules I have to work with. I have the rules that R2 and R3 have the exact same voltage. However, that voltage is not my total voltage, it's whatever's left over from R1. And I should point out that if R1 was down here at the end instead of before these two, it would still be taking up 5.8 volts and you would still have 6.2 volts left. So using that information, I'm going to go in and find my currents. So the current at number 1, well, since this is current at number 1 is in series with my original voltage there, my rules for a series circuit are still the same. So my current at 1 is equivalent to my total current, which is 0.026 amps. So I can use that rule since that is part of my series circuit. At number 2 and 3, they are in parallel. So what I need to do is use my voltage from number 2 and my resistance at number 2 to find my current, because this is now part of a parallel circuit, although it's a smaller, what I would consider a smaller parallel circuit or a mini parallel circuit inside of this because you're only using 6.2 volts. So I'll say voltage at 2 divided by resistance at 2, and that would be 6.2 volts divided by 470 ohms to get a current of 0.013 amps. Now what's kind of nice is since they are the same resistance, I know that it would be half of whatever is left, or half of whatever my total voltage is, because they would have to add up to that total voltage. But we'll make sure we show the work here, because if they were different resistances, you would have to go through this work. So we'll again go 6.2 volts divided by 470, and we get 0.013 amps. And our check for that, again, would be that I2 plus I3 should give us our total current, and it does. 0.013 plus 0.013 gives you 0.26. Our check for our voltages is that R1 and the parallel portion would be in series, so we have 5.8 plus 6.2. That ends up giving us our 12 volts. So we have our check, everything checks out that way using our Kirchhoff's voltage and Kirchhoff's current laws. So when doing a combination circuit, it makes sense that you use a combination of rules from both parallel and series circuits, and hopefully this example will help you to continue doing these problems as you keep working.